Hello, welcome to GeoAI tutorial number 10. In this video, I'm going to show you how to detect solar panels from aerial imagery using deep learning and GeoAI. First, I would like to show you the result. This is a high resolution aerial imagery. As you can see here, I've already detected the solar panel. So the red outlines represent the area of the solar panels. You can zoom in to see more details. When you hover your mouse, you will be able to see all the attributes associated with each solar panels, including area and also some of the geometry properties. And you can also look at the shape. It aligns very well with the actual shape of the solar panels, and it looks really nice. And all you need is just a couple lines of code using the GeoAI package. You can detect solar panels for any location around the globe. Super powerful. So let's dive into it. First, let me show you where to get the notebook examples. You can go to the GeoAI website. The link is in the video description below. And if you want to learn more about the package, you're welcome to click the link, open the YouTube tutorial series. So this is number 10. I've covered from installing the packages to downloading the data and also extract all kind of features, for example, buildings, cars, ships, something like that. So today we're going to do solar panel. If you go to the website, click examples, and then scroll down to find solar panel detection. So click this, and then you can either run this one using Google Colab. So right click, open this one in Google Colab. Make sure that you switch the runtime to GPU. So change the runtime type here, and then click T for GPU, click save. You should be able to run this one using GPU. So it's going to be much faster. Then you can uncomment this line to install the package, or you can up right here, click the download button to download this one to your computer. Then you can run it on a local computer if you have the GPU. So I already have this on my computer here. I'm going to show you how to do that step by step. First, let me clear the notebooks. And so the first step is to import the library. Just shift enter. You'll be going to import the libraries. Next, we want to download a sample data set. So this is a sample data set. I put it on Hugging Face. It's an area covering area imagery covering Davis, California. So let's run this one, and you can call the print raster info function to get some basic information about this imagery. So you can see the size, 6,711 columns. X basically how many columns and rows. And so this is basically the height. This would be the width, 3 bands, unsigned integer. You can also look at some basic statistics if you want to. It also shows you the thumbnail, what the imagery looks like. It's a static imagery. You can use the GeoAI excuse me, view raster function to view the image interactively. And so this is the original imagery. It's 7 centimeter. Again, you can see the information from here, 0.07. So this is meter. So basically it's roughly 7 centimeter resolution, very high. And once you have the imagery, you can zoom in to see there are indeed a lot of solar panels in this area. And once you have the imagery, then we can start doing the detection. So the first step is to initialize the solar panel detector. So this is basically just creating the model using the pre-trained models. And so if you have, this is the first time you're using it, it's going to download the model from Hugging Face. Once it's downloaded, then we can just, using one line of code. So basically utilizing the pre-trained model, call this function generate mask. It's going to, excuse me, it's going to generate the raster mask. So what we need is just the input raster data set. And this one can be, you can provide your own data set, but it does need to be high resolution. For coarse resolution, if humans cannot see that, it's going to be difficult. So at least maybe half a meter, from a couple centimeter to half a meter resolution. Those are usually good quality images that we can see the solar panel. Specify the output. Maybe let me run this one first, and oops, run the first line output, then let it run. So you see here, under the hood, it's going to basically subdivide the imagery into smaller tiles, and then it's going to run through that the model is going to basically do the inference on individual tiles. At the end, it's going to merge all the result. It's a single imagery, so that you don't have to deal with that the nice thing about the GeoAI package is that all the heavy lifting, input, output, and do the tidying, everything, all you need is just focus on getting your input data and then getting a result. That's it. You can specify some parameters here if you want. Unless the results are not very good, you can customize it. So the confidence level will be basically for each polygon that you detected, there will be a confidence level ranging from 0 to 1. So the higher the number, that means the more confident. The more selective, that means the smaller number of polygons you're going to get. And the mask threshold is, in general, the higher number, the outline going to align very well, but you might end up with a smaller number of masks. But sometimes you might end up, if there's missing too many, you might want to decrease the value. Also, you can set the minimum object size, means depends on your object of interest. If you already know roughly, the range of the size of the object that you are detecting, you can specify it, and also the overlap size. Those you can use the default settings. It should be fine. Once you have the results, now we can just call this view raster function to view the result interactively. And so let me show you here. This is the outcome. And pay attention to this one, indices equal to 2. The reason why I specify this one is the output mask contains 2 bands. So the first band is just a binary mask, yes or no, 1 and 0, means whether it's a solar panel or not. And the second band is the confidence, so basically the probability of each detection. And so that's why if you see this map here, it looks kind of a different color, ranging from, for example, red color to yellow color. And this is basically just a color bar. So red color means lower confidence, yellow color means higher confidence. So clearly you can see here most of the buildings, the solar panels, actually they are pretty high confidence. So the yellow is better. And if you upper right corner here, select the solar panels, you can turn this one on and off. So this will be the raster mask output from the models. And if you zoom in and zoom out, you should see, for example, this one here. Some of these red color means the model is not very competent. And certainly you can see some false positive. That means these are not actually solar panels but being detected. Later, I'm going to show you how to filter out some of these false positive objects. And once you have the rasterized mask, we need to actually convert them to vector, because if your goal is to figure out how many solar panels in this area, or maybe you're trying to figure out the total area of the solar panels, then you need to convert them to vector, because right now it's a raster imagery. It only shows you they're all solar panels, but you don't really know how many of them are out there, and you need to run some statistics. So the easiest way would be just to vectorize the mask. You can use just this orthogonal function to convert them from raster to vector, and just one line of code. So the input will be the mask. Output, we can output a GeoJSON here. You can also specify epsilon, basically how smooth you want your polygons to be. This one right now I think works pretty well with this number. If it doesn't work well or be simplified too much, you might want to lower this number. If this is not simplified enough, you want to increase the number. So play with these thresholds, see if it works. There's no universal number that works for all regions around the globe. So you do need to provide some of these parameters. You can press Shift tab to look at the documentation. There are a couple other parameters in here. I don't have time to go into the detail, but you can look at the help documentation to figure out what each one represents. So just run this one and it should be very quick. You see less than 1 second. Now we have this vectorized data. And the reason also we want to do that, because if you zoom in, these are all very pixelated. So if you're trying to directly convert this to vector, the result will not be very good. Even if you can simplify using some GeoPandas and other third-party packages, the result is not ideal, because we want this to be regularized, basically right angle, because most of the solar panels, they look pretty much just like right angle. And if you call this function, you should have good result compared to other methods that you have. Okay, so let's visualize the result interactively to see what it looks. And look at this. So now we have some very nice geometries have been converted to vector, and you will see the value 255. So basically just the binary converted from the raster imagery is just binary, basically 0 and 255. So 255 represent just solar panels. Look at how nice it is. Right now, we don't have the rugged edges from the raster anymore. So this is pretty sharp and clear. They're all vector data set now. And if you zoom in and zoom out, they have been all been orthogonalized as polygons. So you can zoom in and zoom out to see there might be some artifacts. For example, this one is not really solar panels and it's very long. So later I'm going to show you how you can calculate geometry and you can filter out it easily. Also, there's another one here, upper left corner. This one is looked a bit weird compared to the raster. I think the raster output looks pretty good, but for some reason, right now the algorithm is acting weird for some polygons. I don't know why yet. I need to spend more time to debug the source code, but at least for now, for some of the polygons, it doesn't regularize very well, and it's like some small cases. In this case, it's just one single polygon that doesn't simplify very well. So I might need to play with the parameters to figure out what's the optimal that can get the best result. And once we have this, so we need to refine the result. As I mentioned, you can calculate the geometry properties. So all we need is just call the GeoAI add geometry properties and passing the vector data we get from the previous step. Just run it very quick. So now we have these attributes ranging from size, length, perimeter, all the way to, for example, elongation, extent, solidity, complexity. So these are some of the attributes that similar to a scikit image. Again, I don't have time to go into details. You can look at the Shift tab, the documentation here, excuse me, to learn more about some of these parameters. And one of the things that we observe from the previous output is that some of, for example, the artifacts, that one is super long. So we can fix the filter out using the elongation metric. And after we add the geometry attributes, let's take a look at like how many solar panels in this area, right? So this is the initial result. We have 44 solar panels. We can also view them interactively after we added the geometry properties. So this is what it looks like. Now, if you have your mouse, you should be able to see all the geometry properties here, right? So you can get the area in square meters, the length, and also some of the geometry attributes. Now look at this one. Because we're creating a map, we excuse me, using the elongation is basically the column to create the symbology. Upper right corner here, you can see the color. So the elongation ranging from, for example, from 1 all the way to 9. So that means the blue color represents the elongation is not very long. Elongation means basically the major length, axis length divided by the minor axis length. So you can think about minimum bounding rectangle enclose the area. So if it's very long, the elongation is going to be very high. So this one particular polygon, the elongation is 10, right? It's super high. So this one is definitely not normal. So it's less likely to be solar panels. But if you need to look at it, it's not always the case because it might really be true in some areas. So there's no universal threshold that works well for all the locations. Just get the initial result and then you can do the filtering to get better results. Okay, so next step, let's filter the result. And so this is just a simple criteria we're going to use. So I'm going to select all the polygons with elongation less than 10. So that means they're not super long. Also, I mean, roughly, I know in this area, most of the solar panels should be greater than 5 square meters. So you can set multiple thresholds. It all depends on the attribute here. Again, I'm going to go back to this one. It's up to you what you want to use. You can use a combination of multiple criteria. It can be and or it can be or. So up to you how you want to define the criteria. So for me, I will just use the size and also the elongation. Then after this, we filter we decrease the number of solar panels from 44 to 42. So basically we move two false positive. The one is the super long one, the other one is this very tiny one. You can increase this number if you end up with a lot of small objects that are not solar panels. All right, so once you have this, now we have the so-called final result, and we have 42 solar panels in this area. Also, we're going to use the right now for this map, we're going to use the area square meters as the color. So again, the upper right corner here, you can see the color bar. So blue color will mean to represent small size solar panels. Yellow color represent large area. So now we have this map. Take a look. This is what we have right now. Is the final result, and you can see here. This one is like 83 square meters. It's pretty big, but we have some medium size. We also have some smaller one in blue color, and overall, it looks pretty decent. And also the false positive one that used to be here is gone now because we filled it out. And also another tiny solar panels. Again, the only thing right now is this one looks a little bit weird. And I think there's another smaller one here. Also, this looks a little bit weird. This is not a solar panel. And we can use some other criteria to filter out this one based on some other matrix, because this one is kind of a shape is a little bit complicated. So the orthogonalized function it's skipping this one because it's too complicated to, doesn't really have a shape that can easily approximate this one. I think I might need to improve the function to add maybe another column to indicate whether this polygon has been orthogonalized or not. Basically, it has been modified or not. If those polygons are too complicated, that has not been modified, then I might apply a second procedure to either remove them or modify them. Also, I would like to point out the algorithm is not perfect. No AI algorithms are perfect. You still need to verify. So in this case, you will see some of the polygons in here. These two are not detected. So these are basically the missing ones. And the reason for that, it might be it's totally dark and there's no really like other solar panel. You have some patterns inside compared, for example, to some neighboring ones. And so the model doesn't capture this one. Or it can be because of the we set the confidence threshold too high. So this the confidence level might be below the threshold, for example, 0.5, so they're not being detected. Again, you need to play with the parameters to see if you're missing too many, then you relax your criteria to select more. But you don't want to be too relaxed. You will end up with a lot of false positive objects, then you have to filter them out. So it's kind of balanced act. You need to play with the parameters to figure out the best one suitable for your area interest. Okay, so that's the final result. But if you don't want to have a color, you can also just show the outline. So the last one here I'm going to show you is just show them as outline red color. So right now this is pretty obvious, and you can see these polygons align very well. If you hover your mouse, you will be change the fill color to red. And again, you can see all the attributes associated with each solar panel, and this look really nice. You can also actually play this one on the documentation. You will see the map actually is interactive, so you can also, you don't have to run it, you can see the result interactively. It's the same because the notebook is being executed when the website is being built. So you're welcome to play with it using either Google Colab or your local computer. Lastly, let me show you some basic statistics, right? So if you're interested in figuring out, okay, what's the total, what's the spatial distribution, you want to figure out roughly what kind of the size, average size of the solar panels in this area, you can just run this single function. So because it's a geodata frame, so we can actually utilize all the pandas data frame functions. So we're just going to use this area square meters, that column, and then create the histogram. Clearly, you can see the spatial, the size distribution of solar panels in this area. So most of them, I mean, roughly between 10 to 30 square meters. There are some pretty big ones, like maybe up to 80. But you can also describe, for example, the standard deviation, how many solar panels here, the minimum size, the maximum size, also the median size. So roughly the median size is 25.86 square meters in this area. If you want to calculate the sum, you can also do it, 1000 229 square meters, right? So rather than you have to digitize them yourself, because right now there's no open data set that captures all the solar panels at the national scale or county scale, or even, for example, small city scale. So this is something that may be very useful if someone working on the energy sector, we're trying to identify potential customers. You want to figure out, for example, how many solar panels that already have in this area. Is it already too much, or is it just too little? Then you can maybe use some of this. If you already have the data, high resolution, you can download, using the dataset tutorial covered in the second one, to download high resolution area imagery for the area, and then you can just run the inferencing to get the solar panels if this is something that you are really interested in. And the last step is to just save this one as vector data. So you just run one line of code, and then to save this one is GeoJSON. Once you run this one, you should be able to find the solar panels, for example, as a GeoJSON file. So you will see solar panels here, this file just 8 seconds ago. This one you can open it in desktop.js, or you can use GeoPandas or another Python packages to read the data. So sorry about I'm not feeling well today, but this is the tutorial that I really want to show you, and I think this notebook is detection results probably the best one I have get so far from other tutorials. For example, building car detection and others, because the newly orthogonalized function, it works pretty well for solar panel. So I really like this one. I highly encourage you to try it out. So this is the this is the function that I did yesterday, and it looks super well. Again, there's a small room for improvement, but at least for the majority, I think 80-90% of polygons, it vectorized pretty well, and you can get all the geometries. Try it out with also buildings, cars. You can do it for any other object that kind of human shape with rectangular shape. Then the algorithm might work very well. Okay, that's all for this tutorial, and I hope you find it useful. I will see you in the next one.